Related rates. How is it possible to use implicit differentiation to solve real life problems? And the way we do that is we find what I call a primary equation. From that equation, differentiate it using the chain rule, and then from there relate the rates. What rates are we talking about? Well, rates of velocity or rates of acceleration. For this section, there will be simply rates of velocity. How does one side or angle tender or differ in its rate than another side? Well, let us examine that, finding related rates. The example that's given here in the textbook by looking at the volume of a cone, and then from there we can take that volume equation, differentiate it with respect to all variables, v, the radius, and the height. And then from there you're able to relate those rates. And if you're looking for the change in the height, you can solve for dh over dt with respect to all the other variables. If you're looking for the change in the radius, that is dr over dt, then you can isolate it with respect to all the other variables. Here are some guidelines for solving problems using the related rate technique. Basically, you're going to find or determine an equation. I call that a primary equation. From there, differentiate it, applying the chain rule. And then from there, you should also connect with that a secondary equation, which for this section, the secondary equation is a fixed equation from algebra based on the differentiated form that you found from the primary equation. Well, let me show you what I mean by this. Take this problem. A ladder 25 feet long is leaning up against the wall of a house. You see the figure here, and it says that the base of the ladder is pulled away from the wall at a rate of 2 feet per second. So this rate here of the base of the ladder is moving at a rate there of 2 feet per second. How fast is the top of the ladder moving down? That's the direction of r, so we're looking for the rate of r, dr over dt, when the base is 7 feet from the wall, and when that base changes to 15 feet, and then when that base changes to 24 feet. Well, let's look there and see if we can take a spin at it. So I want to take this triangle, and if you can draw a figure, that's probably the best way. This is 25 feet here, r is over there, and x is the base distance of the base of the ladder to the wall. Now notice that they give us this rate along the base of the ladder as it's changing, so that's dx over dt, and so that's 2 feet per second. Now this triangle is a right triangle, so it forms for us this equation, the Pythagoras theorem, x squared plus r squared is equal to 25 squared. Okay. Now we can take that and find all that we want. Now this is going to be our primary equation. From there, if we differentiate this guy using the chain rule, and we're going to differentiate implicitly, so to do that we have 2x times the derivative of x using the chain rules. We get dx over dt plus 2r times dr over dt, and 25 squared is a constant, so that derivative is 0. Now the goal here for this problem for part A is to find, it says how fast is the top of the ladder moving down the wall when its base is 7 feet, 15 feet, 24 feet. So we need to find dr over dt. All right. So we do that first when x is 7 feet. So when x is 7 feet, we use the Pythagorean theorem, or the theorem of Pythagoras. And so we have 7 squared plus r squared is equal to 625. That implies that r is equal to the square root of 625 minus 49. And on your calculator, you calculate that to come out to be 24 feet. And so if that be the case, going back to this equation that we got from the primary equation and we differentiated, that here we want to isolate the dr over dt, get this guy by itself. So we divide through by the 2, that cancels out the 2, subtract x dx dt on both sides, so we have r dr over dt is equal to negative x dx over dt. And so this implies that what you're looking for, dr over dt, is equal to negative x over r times dx over dt. Now I need more space. Okay. All right, let's see if that'll help us out there. So this is when x is equal to 7. So dr over dt is equal to negative 7 feet, right? Over r, and r we got to be 24 feet. And this is times the rate, and the rate there is the dx over dt, that's the 2 feet per second. All right, and so that gives us negative, here this is negative 7 over 12 feet per second. Okay. That looks, so for that, so it's going to be x over r. Okay, good. The next one that we do is, it says when x is 15 feet, use the Pythagoras theorem And so here we have the x squared plus r squared equal to 25 squared. So r is equal to the square root of the 25 squared, which is 625, minus the 15 squared. And on our calculator, that gives us 20 feet. So here, dr over dt is equal to, the formula is negative x over r times dx over dt. So we get negative x, which is the 15 feet, divided by r, which is the 20 feet, times the 2 feet per second. So that gives us the negative 15 over 10, negative 1.5 feet per second. The next one, and so here for the next one, this, it says when x is equal to 24 feet, and that's kind of funny because we got r to equal 24 feet when x was 7 feet. So turn it around, if x is 24, then that means that r would equal to 7. So here, this implies that r is equal to the square root of 625 minus the 24 squared, and that'll give us 7 feet. So the formula dr over dt is equal to negative x over r times dx over dt, and that's equal to negative x is 24 feet all over r, and r is 7 feet times 2 feet per second. And so that gives us here the negative 48 feet over 7. Let's write that a little bit better. Negative 48 over 7 feet per second. It's a little bit better. Why is it negative? Why is the rate of change negative, or the velocity? Because it's slowing down. The rate is slowing down. Okay, here this is consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So again, we consider this triangle, the base is 7 feet. So find the rate at which the area of the triangle, and here we still know from what was given that this is 25 feet, and you know that the rate on the bottom, if we call this x, dx over dt is still given to be 2 feet per second. And so the angle, find the rate at which the area of the triangle, well, we just use the formula for the area of a triangle. The area is equal to 1/2 the base times the height. Now, if the base here is 7, then we had calculated before that if x was equal to 7, that meant that r was equal to 24. So this side over here is going to be 24. Now we take this primary equation and we calculate the derivative. So here this is dA over dt is equal to 1/2 times dB over dt times the height plus 1/2 times the base times dH over dt. Now dB over dt is just going to be the dx over dt, right? And so let's see if we can label these terms. The base is 7 feet. The height is 24 feet. And this dB over dt, right? That guy is the dx over dt. So that's the 2 feet per second. And the dH over dt, when x is equal to 7 and that r was 24, we calculated that already. When the x was 7 and the r was 24, then the dr over dt, which is now the height, the dH over dt, that's the negative 7 over 12. So if that be the case, I think we have everything we need. It said here, calculate the rate at which the area is changing. So we need dA over dt. So that's going to be 1/2 times dB over dt. And we have that to be 2 feet per second times h. H is 24 feet plus the 1/2 times the base. The base we have is 7 feet times dH over dt, and that came out to be the negative 7 over 12 feet per second. And so this dA over dt, this the feet squared divided by seconds, and that's going to be 2 divided by 2 cancels out, so that's 24 feet squared per second. And then this is minus, here this is negative 49 twelfths feet squared per second. And then on your calculator, calculate that. So 49 over 24. $49 over 24 feet squared per second. So that gives us 527 over 24 feet per second, or 21.96 feet squared per second. Okay. All right. Let's look at the next one. Part C, find the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. So we have this right triangle. Let's claim this to be theta. That's the angle that we're looking for. Here, the base is 7 feet. It says find the rate at which the angle between the ladder, and this is the ladder again, and this is 25 feet. That's fixed. If the base was 7 feet, we had found before, is based on the same problem, that that height, the side of the wall is 24 feet in terms of the ladder. Right, 24 feet. Now, to use the angle and at what rate is this angle changing, you can either look at the tangent theta of this or the cosine. Anything that's going to relate the change in this side over here with respect to theta. We could not use the sine because the sine would be the opposite over the hypotenuse, and that would not tend to the rate of change as this ladder is being lowered or raised. So I'm going to use, I think easier is to use cosine. So cosine theta, if you look at that, and again, at 7 feet, this side is 24 feet, but it tells us here that the 7 feet is fixed, but this side over here is not fixed. So there's some change there. So I think it was called R. So I call it R here as well. So the cosine theta is the adjacent over the hypotenuse. That's R over 25. That implies that 25 cosine theta is equal to R. Let's take this equation and differentiate it using the chain rule. So we get negative 25 sine theta times the derivative of theta. That's d theta over dt with respect to time. That's equal to dr over dt. We're solving for this change in theta. This is the d theta over dt. So d theta over dt is equal to negative 1 over 25 times 1 over the sine theta times the dr over dt. Now sine theta here is the opposite over the hypotenuse. So you can calculate sine theta as being 7 over 25. And the dr over dt, we found that from the first part when x was equal to 7. That's negative 7 over 12 for dr over dt. So the d theta over the dt is negative 1 over 25 times 1 over the sine, so that's 7 over 25, times this dr over dt, negative 7 over 12, and so the 7's cancel out, the negatives cancel out, the 25's cancel out, and you have left 1 over 12. This is going to be in radians per second. Okay, and my writing is kind of going up. So d theta over dt is equal to 1/12 radians per second. Well, let's move on. We spent a lot of time on that problem. All right, let's see. A construction worker pulls a 5-meter plank up the side of a building under construction by means of a rope tied to one end of the plank. See the figure. Assume that the opposite end of the plank follows a path perpendicular to the wall of the building, and the worker pulls the rope at a rate of 0.15 meter per second. How fast is the end of the plank sliding along the ground when it is 2.5 meters from the wall of the building? So let's see what we have. So they give us the rate going up and down, right? So I'm going to call this side X and we'll call that side Y. And thus, this plank is fixed at 5 meters. It says, how fast is the end of the plank sliding along the ground? That is, find dx over dt. Again, we form a right triangle, so we use as our primary equation the Pythagoras theorem. So here we get x squared plus y squared is equal to 25, that 5 squared. We take the derivative. Here we get 2x times the derivative of x dx over dt plus 2y times dy over dt is equal to 0. And so since we're looking for dx over dt, if you isolate that and get that by itself, divide through by 2, we have y over x, and it's negative dy over dt. Very similar to the previous problem. So let's see. They tell us something. They said, how fast is the end of the plank sliding along the ground when it is 2.5 meters from the wall of the building? That is, when x is 2.5 meters, they give us that. X is 2.5 meters. So if x is 2.5 meters, we can solve for y using Pythagoras. So y is equal to the square root of the 25 minus the 2.5 squared. And on your calculator, if you calculate that, that comes out to be 4.33. And this is in meters. So it looks like we have everything we need. Oh, by the way, the dy over dt is the 0.15 meters per second. That's the up and down motion. So the dx over dt is the negative y, which is the 4.33 meter, divided by the x, 2.5 meters, times this rate dy over dt, and that was 0.15 meters per second. And on your calculator, you calculate that, and that comes out to be negative 0.26 meters per second. Okay. Okay, so been having some technical trouble with the platform in which I record these lectures in. I don't know what's going on. The pen has been going out on me, and I had to pause and kept on pausing this, trying to fix it. So hopefully it's fixed. Number 25, an air traffic controller spots two planes at the same altitude converging on a point as they fly at right angles to each other. Oh, how interesting. This is for number 25. So it's this side right here. One plane is 225 miles from the point, moving at 450 miles per hour. The other plane is 300 miles from the point, moving at 600 miles per hour. At what rate is the distance between the planes decreasing? And how much time does the air traffic controller have to get one of the planes on a different flight path? So let's see. Let's say that this is X down here, and this is Y. And it looks like the X is going to be the 225 miles. Yes. So X is 225 miles. And the dx over dt is going to be the 450 miles per hour. And then the Y is the 300 miles, and its rate is 600 miles per hour. Right? And let's see, anything else we need from there. We get S. We can calculate S by using the Pythagorean theorem. We can get that value. So, but this tells us when the plane is 10 miles away. Oh, this is a different problem. Okay, we're back up here. Okay, so we can calculate S. So, what are we looking for? At what rate is the distance between the planes decreasing? That's S here. So if the planes are decreasing, then we should negate the rates here to denote that. Okay. And looking at Pythagoras, and by the way, this is for number 25 that we're doing. So x squared plus y squared is equal to s squared. And here s is not a fixed point. S is changing. So it gives us a little bit more to work with, but it's no problem. We can do it. So we differentiate. We get 2x times dx over dt plus 2y times dy over dt is equal to 2s times ds over dt. The rate of the change of s, that is of the difference between the two planes, is the ds over dt. So here you want to find ds over dt. Right? Divide through by the 2 and also divide through by the s, and we can get the ds over dt by itself. So this is x over s times dx over dt plus y over s times dy over dt. Now the s can be calculated by using Pythagoras. You know that x is equal to 225 and then the y is equal to 300. So s is equal to the square root of 225 to be squared plus 300 to be squared. And that gives us a value for s as 375. And what are we talking about? Is this in miles? Yes. So we can calculate ds over dt. So this is x over s. X is the 225 over s, that's 375, times the rate of change of x, 225, and it's negative, by the way. Then plus y, which was the 300 miles over s, 375 times its rate, negative 600 miles per hour. And then you calculate that, and that gives you on your calculator. It's my cell phone. I need to put that on silent. Pretty cool sound. The good, the bad, you can't beat it. Negative 750 miles per hour. Why is it negative again? It's decreasing, right? That distance is diminishing. Then, this was part A, by the way. So part B, it says, at how much time does the air traffic controller have to get one of the planes on a different flight path? So we're looking for the time, and since we know that the rate is equal to the distance divided by time, this implies that time is equal to the distance divided by the rate, of which both quantities we've already calculated. So the distance here is this 375 miles, and its rate was 750. That comes out to in half an hour. or 30 minutes. Let's play some baseball. I will conclude with this problem, number 27. A baseball diamond has a shape of a square with sides 90 feet long. A player running from second base to third base at a speed of 25 feet per second is 20 feet from third base. At what rate is the player's distance S from home plate changing? Now we got to draw that out, I think. So this side here is fixed at 90 feet. This is going to be S. So a player running from second base to third base at a speed of 25 feet per second is 20 feet from third base. So this side right here, let's just call it X. And so we get X is 20 feet. And the rate for X, dx over dt, they give us that to be 25 feet per second. We need to calculate, it says here, at what rate is the player's distance S from home plate changing? So you need to calculate ds over dt. Find ds over dt. Right. Well, since this is a right triangle, we have 90 squared plus x squared is equal to s squared. Now we can use the fact that we know that x is equal to 20 to calculate s. So we get 90 squared plus 20 squared is equal to s squared. This implies that s is equal to the square root of 90 squared plus 20 squared. And you calculate that on your calculator. And that gives us, I thought I had written it down somewhere. Ten times the square root of 85. Okay. So now, to find this derivative ds over dt, we take this equation and we apply the chain rule. So when you take the derivative of that 90 squared, that's just 0. So here we get 2x times dx over dt is equal to 2s times ds over dt. So the ds over dt is what you want, and that's equal to the x divided by s times the dx over dt. And so here, ds over dt is equal to the x is 20 feet. That's divided by s, and the s came out to be 10 times the square root of 85. And the dx over dt, we have that as 25, this is feet here, 25 feet per second. And when you calculate that, it comes out to give you 5.423 feet per second. And let's see. Whoa, oh, this is baseball. I almost forgot. This guy, he's running from second base to third base. He's slowing down. And if that third baseman is in the way, he's gonna get knocked out. But this guy, this runner, he's slowing. So his rate, 25 feet per second, is negative. Oh man, you can't forget that. I'll tell you, I hadn't played that baseball in so long. So this is negative, and so the result is negative. Okay. So that was 27. Well, I guess that should do it for now.